Okay, I am going to explain at my current level of understanding, um, one, how hypothesis testing works, what's up with p-values, and two, how we derive standard error, which, as we'll see, is related. So basic situation here is, let's say that we have some effect that we want to test. To use an example that's similar to one that I've actually had, suppose that I'm trying to improve my typing speed, and I hypothesize that uh, taking some, what I hypothesize that fasting improves my typing speed. If I don't eat for the day, then I will um, type faster. So how do I test that? Um, so the first thing is I have a population or a distribution of typing speeds. So sometimes I type like exceptionally quickly, sometimes I type especially slowly. Most of the time it's in the middle. It's nice Gaussian. We have a mean right here. And so the first thing that I want to do is I want to take a sample that is, I want to take a sample, some number of data points, like individual little typing tests where I see how fast I can type, um, and I want to see what that sample comes out to. Um, right, so I'm not modifying anything. I'm not fasting for this time, and so I'm expecting that the sample that this sample, this control sample, as it were, is going to come out somewhere around the mean. Of course, let's say here. This is mu hat 1. And this is mu. I'm going to take another sample of the same size. It must be of the same size. That is my typing while I'm fasting or whatever. We'll use a different color for that one. And let's say that comes out over here. U hat 2. Now remember that these two mu hats are sample means. So we take a number of data points, and we're taking the average of those data points. So that actually both of these are sort of their own distributions. These mu hats are summary statistics for distributions of samples. And so now we have the question, like, how... Now we want to know, can we conclude that fasting does in fact have an impact on my typing speed? And at first, like naively, we might look at it and say, well, it sure seems like it when we, this is pretty far out from the population mean. The unmodified one is pretty close to the population mean. It seems like, yes, that seems correct. However, there's a couple of things about this. So for one thing, we don't usually have privileged access to the true population mean. It's there, it's real, but we don't know what it is, And so we can't refer to it to determine whether or not a result is significant. So actually, we don't know the whole population. We just know that like when I'm not fasting, and we take a sample, the average is here, and when I am, the average is here. So what can we conclude? And the key to this question is that we want, how do I say this? Well, basically, we're going to assume that this sample is a good all right. So how to say this? We don't have access to the true population. All we have access to is these two samples. We have their distributions. We have how spread out they are. One of them probably looks something like this. Oh, that's pretty fat-tailed. And one of them looks like this. And we want to know, could we have gotten this result by chance? How likely is it that the reason, right? So for all of these, we have some signal, we have some noise, right? Mu hat 1 is not exactly equal to mu, and that's because there's just some randomness mixed in. And so the question is, could this difference between mu1 and mu2 be solely due to randomness? Or is it likely that it is picking up on a signal? And in order to answer that question, we want to know that the statistic that we need to use to answer that question is the standard error. And standard error means the standard deviation of the sample means. So that is to say, we're going to take, if we took a sample of a given size and we average them over and over again. So we have some procedure, and the procedure is this is the procedure for getting a standard error. One, take a sample of size n, where we could set n to whatever we want, but it has to be the same for running through this whole procedure. Take the mean that sample. Use that mean of mean as a data point. And then repeat, do this x times. Well, maybe we shouldn't say x times, because that would say xx. We repeat m times. And then 4, we take the standard deviation of all of those data points. And this gives us a nice, this gives us another bell curve when we do this procedure some number of times. We end up with a very spiky distribution. Right around the mean, because we end up with the very spiky distribution right about around the mean, because of course the average, the mean of all of the means, is just equal to the population mean. But because we are taking multiple samples and putting them into the mean, we expect to get each mean is going to be closer to the each sample mean is going to be closer to the population mean than a single data point, right? If I take a single data point, it's maybe way out here. But if I take 3 data points and I'm going to average them together, maybe I get one way out here, but I'm just as likely to get one way out here, or one here, and altogether that's sort of like an anti-extremizing effect. And so we get things that are much closer. We get if we're taking the sample mean, because we're doing this averaging, we get data points that are much closer to the true population mean, that are less spread out than the true population. And so having this distribution, we can then ask what's the standard deviation of that distribution. And this matters. I'll get to how we... I'm going to explain how we get standard error, how standard error is defined in the next video. Actually go through a proof of why it's defined the way it is. But this is the reason why we care about this is because the standard deviation here is telling us how much sample means vary. So that means that's the thing that we can compare to what the standard error is the thing that we can compare to determine how extreme how unusual a given sample mean is, right? So again, most of the sample means are right here near the mean of the population. But let's say, I don't know, one standard deviation of them are fall at around it looks like mu1 is about 1 standard deviation out, and mu2 is multiple standard deviations out. And we can normalize this. This is where we're going to end up with p-values. We can normalize to the standard error. So yeah, you do some things with z-values. You're like where you sort of abstract out the units, and you ask how far along this bell curve are these two things. Yeah, how far along the standard error bell curve is mu1, and how far along the standard error bell curve is mu2. It's actually going to be a little bit tricky with mu1 because we're going to assume that mu1, given the way that we're going to define standard error, mu1 is going to be the center of. It's going to mu1 is going to be centered on. Yeah, our estimator for standard error is going to use mu1. So maybe we should talk about that next. Basically, we're going to take the standard error, and then we're going to use that to standard. We're going to use that to standardize. So we got a bell curve, and then we ask for the. We're going to. I'm going to skip over talking about how we get standard error for a moment, and I'll come back to that. We have this bell curve, and we ask for the experimental group, how far away is it from the mean, from the mean of the means? How many standard deviations? And like so our experimental group might be here, or it might be here, or it might be here. And each of these have like different amounts of how surprising they are. Which we can sort of roughly assess via standard deviations. More standard deviations is more surprising. So if our experimental value, our experimental sample mean, the mean from when I my typing sample, the average of my typing samples when I'm fasting is all the way over here, let's say 3 standard deviations. That is the thing that I can do with that is I take how many standard deviations this is. Um, 3 sigma. It's a sigma, not a 6. And then we can put that into a p-value calculator, which I guess works via some math that I haven't looked at yet. And the p-value calculator just asks, what is the probability of getting a 3 sigma result purely by chance? You could do two-tailed because then you're asking, what's the probability of getting a 3 sigma result or more in just this direction? That would be one-tailed. Or what's the probability of getting 3 sigmas or more, or 3 sigmas or less? But the thing that it's doing is just normalizing, finding a z-score, using the standard error, not to the standard deviation. Not the standard deviation of the population. Instead, the standard error, which is the standard deviation of the sample means. And is asking how unlikely that is. And so this makes sense because the key thing is this bakes in our sample size. If I have a very large sample size, I expect that my I expect these two mu1 and mu2 to converge towards each other. Because there's less room for noise Uh, and if I have a small sample size, then I expect M1 and M2 to be much more spread out because there is more room for noise. And so standard error sort of allows you to measure how spread out would you expect points to be by default if they were drawn from the same distribution. And when you get something that's way over here, you're like, well, this would be very surprising if it was drawn from the same distribution, so probably it wasn't. Probably the fasting actually had an effect. Okay, I think that was, that feels a little bit of a mess, but let's start with that.